Hey, I will present the paper Adaptive Compressed Sensing with Diffusion-Based Posterior Sampling for ECCV 2024. In image processing, images are usually acquired and then immediately compressed to a lower representation. This is wasteful, therefore a technique named compressed sensing attempts to optimize the measurements to make the acquisition of signals more efficient. In our setup, we attempt to use low-dimensional vector of measurements, y, to solve the ill-posed equation and restore an image x. Classic compressed sensing offers several options for the sensing matrix H, which can use minimal rank, or rows of H, and is usually composed of a set of orthogonal vectors. Adaptive compressed sensing constructs the rows of the sensing matrix H sequentially, incorporating information from earlier measurements for the new rows. We introduce AdaSense, adaptive compressed sensing, using diffusion models. We assume we already have constructed k orthogonal rows of H. We now want to find the best next row. The optimal choice is to measure the direction where the uncertainty is greatest. This direction corresponds to the largest eigenvector of the posterior covariance. Using a diffusion-based posterior sampler, we sample valid solutions to the inverse problem from the posterior distribution. The direction of largest uncertainty has the most information, so we sample by projecting the image along this direction. The largest uncertainty is also the largest eigenvector of the covariance matrix, making it easy to find. We add the new sensing direction as a row of H and proceed. As a byproduct of our sampling method, our new row is orthonormal to all previous rows, in line with our conditions for the next step. We can extend this framework to operate in chunks of rows instead of single rows. This diagram shows the cyclic nature of our algorithm. We generate samples with a posterior generative model. We evaluate the best measurement based on the covariance matrix. We measure our image along the chosen direction, and we repeat this process with a new sensing matrix and measurements. Ultimately, one can use the acquired measurements to restore the image, including diffusion-based restoration. The posterior sampling step can rely on one of many zero-shot posterior samplers. In this work, we use DDRM, but many alternatives exist. Moving on to our results. Here we attempt to measure an image using only 192 measurements. If we use a simpler approach, such as downsampling, naive restoration is blurry. If we use deep restoration, with DDRM for example, we get better image quality, but much of the original detail is lost. A better approach would be to use PCA to find a good sensing matrix, but this remains non-adaptive. With AdaSense, we create superior image-specific sensing matrix. The restoration preserves fine and semantic details, as highlighted. Qualitatively, we verify AdaSense outperforms its alternatives. Beyond general measurements, many real-world applications for compressed sensing are constrained to specific sensing matrices. Such examples include MRI and CT. In this example, an MRI image is subsampled in the K-space using the following mask, speeding up the acquisition process. The naive restoration is blurry but can be improved with image processing. The subsampling both speeds up the measurement process and reduces patient dosage in methods like CT. In these cases, we can practically only measure in specific directions. We modify our algorithm to only evaluate in our closed set. Here, we show examples for MRI active acquisition. Using the mask generated by the model, we restore the subsampled image. Compared to alternative methods, our restoration error is lower, as seen here. Our model is on par with competitors for many subsampling schemes, despite not having been trained specifically for active acquisition or having seen any partial or degraded data during the diffusion training. AdaSense is on par with RL-based active acquisition methods. Unlike alternatives, AdaSense is not limited to certain initial measurements or to vertical frequencies alone. Here's another example for CT images. The added performance using our model may be of value in medical diagnostics. In conclusion, we propose a novel adaptive compressed sensing algorithm which we name AdaSense. We use pre-trained diffusion models with no added training. AdaSense can be used in many applications, including medical image active acquisition. In preprint work, we extend our algorithm to image compression. Using the same principles and back-to-back AdaSense algorithms, we can employ the measurement as image-specific compression scheme. Our results compete with classic and deep compression methods while employing only off-the-shelf diffusion models. Thank you for listening.